So we have discussed about some introduction to potential energy surfaces, and there we discussed that a point on the potential energy surface exists, that is a saddle point, in the sense that along the reaction path there exists a maxima, but in all other direction sitting at the minima with respect to the potential energy surface. So at that saddle point, you can think that a transition state between the reactants and the products occur, and what Henry Eyring and Michael Polanyi argued is that if we can study the statistical properties of this transition state, we can actually calculate the reaction rate. Now, before we go through the details what is the derivation of this transition state theory, let me give you a reminder that the rate constant is expressed experimentally, which is the Arrhenius equation, as this: a to the power minus Ea by RT, where A is known as the pre-exponential factor. Now, we do not Arrhenius actually did a lot of experiments, and from that he figured out this empirical relationship, and where this Ea, he said it's a minimum energy required for the reaction to occur. That's known as activation energy. Now, A is the pre-exponential factor, and we will calculate A here. And also, just to remind you that from collision theory, we already found, which we did not derive in this course, which is derived in the earlier version of this course, is that in collision theory expression, it will be something like the total cross section times the average of the relative velocity times e to the power minus E star by RT. So, where E star is the minimum energy in the potential energy surface that we cross. Now, there is a difference between E star and Ea. Ea is an experimentally determined quantity, and E star means if you have a reactant to product going like this. So, E star classically means this difference in this minimum energy that you require from going from reactant to products. This is the product here, reactant to the transitions through the transition state. Now, in this case, which you will see that we can actually think in a more rigorous way that both the reactants as well as the transition state has some vibrational structure, and in that case actually the E star denote the difference in the 0 point energies. So, that correction will be made here. But whatever is the situation for a two body collision like A plus B, where A and B are structureless, it should give me back to the collision theory rate expression, provided the A and B are kind of structureless hard sphere. So, under hard sphere approximation, remember we got this relationship where sigma total is again pi B max square, where B max is the addition of the radius of the two bodies, and V relative also has a expression, and average velocity expression is 8 kbt by pi m, and since it's a relative velocity, we have to replace m by mu raised to the power half. Now, we should get back this expression if we use the transition state theory and if we apply the condition of hard spheres. Now, let us proceed. So, what Henry Eyring and Evans and Polanyi, Henry Eyring and Meredith Evans and Michael Polanyi proposed around 1935-37 is that the transition state exists, which they denoted as say AB dagger, for a bimolecular reaction between A and B, and they assume that this transition state is basically in equilibrium with the reactants, which are the two molecules, and then eventually the transition state forms product. So, this kind of equilibrium is very known to you, which already discussed when we discussed the pre-equilibrium or equilibrium approximation. So they said that there is a pre-equilibrium that exists between the reactants and the transition state, and then the transition state forms the product. Now for if we assume that thing, then we can actually right away apply the equilibrium approximation, which we had already done and we know how to do it. Secondly, what is this rate of product formation? Now you know that this equilibrium approximation will hold if this step, the K2 is very slow, or the second step or the rate step of the product formation is much slower. Now usually that means that whenever I form a activated complex, according to their nomenclature, this is called as activated complex. So this activated complex, which we are denoting as AB dagger in a third bracket, and this activated complex, we can actually remove the bracket right now, because usually we are using the bracket notation for the concentration. And so they said that this AB dagger is a very short-lived species, and then once it vibrates along a particular degree of freedom, which is along the reaction coordinate, each vibration will give me a reaction. Now what does it mean? Let us actually go back to our discussion on atom diatom collinear reaction and try to actually explain it. What do you mean by this vibration of this AB dagger? Okay. Now for that, let us try to draw the two-dimensional contour diagram of potential energy surface once again. Now suppose again I am plotting the AB distance along this direction and BC distance along this direction, or maybe we can actually do the reverse. It will be clear why I am doing the reverse thing. And the BC distance we can plot along, say, x-axis, and along the y-axis I am plotting the AB distance. So around here, when the AB distance has the equilibrium bond vibration for AB, so this position corresponds to basically a stable AB molecule plus a C is attacking. Similarly, along BC, if I say that this is the equilibrium distance, R equilibrium for BC bond, so this position denotes somewhere where I have the BC molecule and plus the A atom, something like that. Now where we are starting from, say, here. This is our reactant, and this is our product. So we can actually draw, I mean, very schematically the potential, very qualitatively, the potential energy surface. So again, these lines actually corresponds to where the energies are same. These are isoenergetic surfaces, and then there is a barrier along the reaction coordinate. Now if you look at this region, when actually we are crossing the transition state, how the motion looks like. So as I have drawn here, I have AB plus C here, and I have A plus BC here. So the path will be something like it is rising and then crossing and the barrier, and it is reaching here. So this path is something like this. Now right here, what is the kind of motion it has? As you can see, it has to move the reaction. If it has to move, it is moving kind of diagonally. Now what is this motion? Let us think about it. Now what are the coordinates here? So in the x-axis we have plotted BC vibration. In the y-axis we are plotting AB vibration. So think about it, like I had initially two vibrations. So the stretching of this AB plus C, and in the final product region I have basically A plus BC, and I have the stretching vibration for the BC. So which are actually vibration for this zone and this zone. Okay, but near the transition state, actually I have something like a structure like this, ABC. It's a collinear atom diatomic molecule again, and again remember that this is neither being broken and this is neither being formed. It's actually in between. Now this complex, which they called as activated complex, has now two bonds. So similarly, if you do a normal mode analysis, you can actually expect two vibrations. One is symmetric vibration, one is antisymmetric vibration. Now what is symmetric vibration? Symmetric vibration means both the AB and the BC actually stretches simultaneously. Now here's the beauty. So along this direction, along say X direction, I have BC vibration. Along Y direction, I have AB vibration. So along the transition state, I am saying that okay, it is neither X or Y vibration, but rather a vibration which is along this. If I move along this, as you can see, both the AB and BC are stretching to the same extent. Something like you had a coordinate system like X and Y, and I am converting this coordinate system into a new coordinate system where actually I have X plus Y, something like that, where both the X and the Y are simultaneously varying. So this is nothing but the symmetric stretch. And then I can also think about another motion orthogonal to it, which is the asymmetric stretch, because if you think that the molecule is vibrating along this direction, the AB molecule is vibrating, so what will happen? So this vibration means, if you can think that I have a rectangle like this and I am vibrating along this rectangle, which is this direction, you can instead of X plus Y, we can actually write it as something like in our original notation, which is R BC plus R AB, which is the symmetric stretch. So it is moving like this, but the reaction happens, as we saw, along this direction. So that's an asymmetric coordinate. Why? Because as you can see, if I move along like this, if I draw it once again, if I move along like this, so if I keep on moving, as you can see that this distance is shortening, but this distance is increasing. So this is the asymmetric vibration that gives you the product, and which is very obvious, because you had A, B, C, something like that. If you symmetrically vibrate, nothing happens, but if you asymmetrically vibrate, so at the BC bond compresses and the AB bond stretches, so that stretching will lead to a breaking of the AB bond and formation of the BC bond, something like that. So those kind of vibrations are actually the asymmetric stretch vibration of the ABC molecule. So basically what we said, that the ABC had sets of vibration which cannot be explained like just a BC vibration or just a AB vibration, which has basically a combination of AB vibration and BC vibration, which gives rise to the normal modes, and that's the meaning of normal mode. You do not have actually isolated AB vibration or BC vibration. You can think of the entire problem like the AB and BC both are vibrating together, but whether now they are vibrating together in a symmetric fashion or in phase, or they are vibrating in an antisymmetric fashion or in an out of phase way. So this coordinate is nothing but something like RBC minus RAB. So it is nothing but a kind of coordinate transformation at the transition state, because as you can see from the geometry, in the transition state you diagonally cross the potential energy surface. You have to cross it because you are vibrating like here as AB, and then you have to vibrate like here as BC. So you have to somehow cross the trajectory has to cross diagonally. Now the question what Eyring and Polanyi and Evans they asked is that if I have this kind of situation, then I can actually apply statistical mechanics to understand what is the frequency of this vibration and what are the statistical properties of this vibration. From this very fundamental assumption that there exists a pre-equilibrium, and since we are talking about all the statistical properties of this molecule, which is AB dagger, again do not confuse with AB dagger. In our here actually I am talking about bimolecular collision, and we already talked about atom diatomic collision, which is something like this. So the A in our notation can represent AB, the B in our notation can represent C, something like that. So this together right now I'm writing as A, this I'm writing as B, something like that. It may be two diatomic molecules also, it may be two polyatomic molecules, it doesn't matter. That's why I'm just using AB notation. So there is no inherent assumption that how big is the molecule. It's just a bimolecular collision, and all of you know that fundamentally these elementary reactions are mostly bimolecular in nature, because for unimolecular reaction also there is a bimolecular reaction that precedes the unimolecular reaction. So bimolecular reactions are at the heart to understand chemical reaction dynamics. Now since we are talking about this activated complex of the two molecules, we call this version of transition state theory as activated complex theory. And again, it was put forward by Henry Eyring, Meredith Evans and Michael Polanyi. Now, what will be the rate constant if I actually apply the pre-equilibrium condition? Now, all of you know that we have already derived it. The observed rate law will be nothing but a combination of rate law, which will be K2, K1 by K minus 1. Already we showed it. So, according to Eyring and Polanyi, what we have to now calculate is this in terms of this rate constant, can we actually get some other parameters with which we can actually calculate the observed rate law. Now, what is K2? K2 is the frequency at which the transition state breaks into the product. So, the idea is that here we are talking about only A plus B two product irreversible reaction. So, here the assumption here is that I had an ABC adduct, and if at the transition state, and then it can vibrate symmetrically, that will not give me reaction because that motion is orthogonal to the product formation. So, if it vibrates like this, so nothing will happen. So, it will not give me the reaction. So, it is a stable vibration of the transition state. However, if it vibrates asymmetrically, it can, now you can argue always that it can vibrate asymmetrically, something like the BC bond is stretching and then again C will fall apart, then actually we will go back to the reactant side. So, that is why I was saying that it is kind of in equilibrium with the reactant also. But if it vibrates in the other way, meaning the AB bond is stretching too much, then actually it will fall apart, the A and B will fall apart and the BC will form. So, the assumption here is that per vibration of this asymmetric vibration, if it goes in favor of the product side, it will give me a product, or if it gives me a if it is something like that, the BC bond is stretching too much, it will give me the reactant. So, it will survive only over the time period of this asymmetric stretch vibration for a collinear atom diatomic reaction. But for in general case, they said that there will be one particular vibration. If it vibrates once, it will immediately form either the reactant or the product. So, the frequency of the reaction, which is the K2, is nothing but identical to a particular characteristic frequency which is along the reaction coordinate, and that frequency let us denote it as nu dagger. Now, K2 is a rate constant which is a bimolecular rate constant. The overall bimolecular rate constant is K1 by K minus 1 into K2, and nu dagger, if you remember, that has a unit of second inverse. So, we can actually approximate nu dagger, we can say that nu dagger also has a dimension of a rate constant. Now, what we are saying here is that, okay, fine, so that is the value of K2, and what about K1 by K minus 1? Now, already we know that K1 by K minus 1 is nothing but an equilibrium constant, the equilibrium between the reactants and the transition state. Now, from our previous classes on statistical thermodynamics, we know that I can write the equilibrium constant in terms of the molecular partition functions of the reactants and the products. So, it will be partition function of the products first. So, the product I denoted as QAB dagger. Remember, it is actually the partition function per unit volume, and divided by the partition function per unit volume for the reactants. So in this case it will be something like this, and times I have a factor where this E star denotes the differences in the 0-point energies of the reactants and the transition state that we also discussed. So in the equilibrium constant, when I discussed about A and B are in equilibrium, where A and B are both molecular species, there we said that it will be the 0-point energy difference. In this case, it's the 0-point energy difference between the reactants and the transition state. So the reactant has some vibrations and the transition state also has vibration, but remember that these vibrations are orthogonal to the trajectory, because along this direction if it vibrates it will just fall apart. So right now I am talking about all vibrations in the transition state. So this 0-point energy difference is the E star here. Now think about it, among this Q, the partition function for the transition state, which we denote as Q dagger by AV. So it contains translation, rotation, vibration as well as electronic partition functions. Now we can write it as, okay, so it will be composed of something like Q translation of the AB dagger. Usually we associate the volume with Q translation. It will be times this Q rotation of AB dagger, then it will have Q vibration of AB dagger, and then there will be also electronic, but usually in this case I will say the electronic partition function of is 1, but we are just keeping it for the time being. Now you can think among all these vibration, one vibration is along the reaction coordinate, along this arrow, and all other vibrations are orthogonal to this reaction coordinate. So we can actually split this vibration into two parts, where we will calculate one vibrational partition function for that particular vibration which has a frequency nu dagger, because nu dagger is along the reaction coordinate. Now what is the expression for vibrational partition function? It is 1 by 1 minus e to the power minus h nu by kBt, 1 minus e to the power minus, here it will be h nu dagger for that particular partition function, and the rest of the thing I am just writing it as Q vibration by AB dagger, and I am using a prime notation. This prime means it is basically the partition function, vibrational partition function, except one degree of freedom. Which degree of freedom? That degree of freedom which is along the reaction coordinate and which has a characteristic frequency which is nu dagger. Now what we are going to do, we are going to collect all these terms together and write basically Q, the entire thing I am writing it as Q AB dagger by V prime times this particular term which we separated out. Now this can be evaluated very easily. How? Because I have e to the power minus h nu by kBt, so that we can expand as 1 minus h nu dagger by kBt. Now why I am truncating up to, it is a series expansion up to the second term. The reason is, as I said, that this nu dagger is a low frequency vibration. Why? Because I said that for the equilibrium approximation to be valid, the K2 or the rate of product formation has to be slow. So it is not very surprising also, because you can think that this is an asymmetric stretching vibration which has a much slower frequency, and once it vibrates it falls apart. Now that is why this nu dagger or h nu dagger is much smaller compared to the kBt, which is the thermal energy, and then we say that okay, so we can actually ignore the higher order terms. The moment you make this approximation, this entire thing, it is 1 minus e to the power minus h nu by kBt, that actually becomes 1 over h nu by kBt, or the entire thing becomes kBt by h nu dagger. So we see that the this partition function for the activated complex, which is the AB dagger, has a form of kBt by h nu dagger times all other partition function together, which we can calculate, of course, using statistical mechanics, and we will give you an example where we will calculate. And but there is 1 degree of freedom less. Which degree of freedom? That particular vibration which is along the reaction coordinate and which is much of slower frequency and which has a characteristic vibration of nu dagger. Now we can put back this into the equation. So the original equation, if you remember, we had the observed rate, which is k2 by k1 by k minus 1. So for k2, I will replace it directly with nu dagger. So what we get from the transition state theory is that it is k2, k2 is nothing but nu dagger, times k1 by k minus 1, but k1 by k minus 1 was connected to the equilibrium constant, which is connected to this combination of these partition functions times this exponential part, and among this I replaced this part, which is q AB dagger by V, by this expression kBt by h nu. Let us just put all these things together. So I had the partition function of the products, which is q dagger by V, but then we took out one particular degree of freedom. That's why I am putting the prime thing. For the reactants, we did not do anything. So it is q A by V, q B by V, these are all partition functions, times e to the power minus E star by kBt, and then that extra degrees of freedom we got the value as kBt by h nu dagger. As you can see, the kBt will now get cancelled out, and then what will be left to it is the famous Eyring equation, which is kBt by h into q AB dagger divided by V, q A by V into q B by V into e to the power minus E star by kBt. So this is the expression for the transition state rate constant, and it has right now has no similarity with the rate constant which we got from collision theory. Now we will see that these two are equivalent, but before that we will do one more thing. So we can actually again remember that we wrote it in terms of the equilibrium constant, and then we can again write this entire thing as an equilibrium constant, in the sense that it is something like kBt by h, but this equilibrium constant is slightly different. It is not exactly the same equilibrium constant for the transition state, but it is the equilibrium between reactant and a transition state, but with 1 degree of freedom less. So that is why I am putting it as a prime sign. Okay. So you can actually look at it, look at the similarities between this equation. So initially I had it is nothing but k2 into k equilibrium from this equation. So we had k2 into k equilibrium, where the equilibrium is between the reactants and the transition state, and now I cleverly actually have taken out 1 degree of freedom, which is along the reaction coordinate, because I expressed it in terms of the partition function, took out that degree of freedom, again recombined the partition functions, and again writing this entire thing as a equilibrium. But this equilibrium is not exactly the special, it is a special equilibrium. It basically does not have one particular degree of freedom. Now this expression also will be useful for discussing some important factor, which we will see soon. First we will see what will be the expression for the transition state theory for a bimolecular reaction where the molecules are structureless.